Hello everyone, this is Ashraf from Sri Venkateswara College of Engineering, studying in 4th SEM. Today I am here to present you a video assignment on Introduction to Quicksort and its time efficiency. So Quicksort is a popular and efficient sorting algorithm. If you have learned the merge sort and other sorting techniques, you could have known about the quicksort. So this quicksort algorithm used to arrange elements in a specific order. It may be ascending to descending or descending to ascending. It works by selecting a pivot element from the list and partitioning the list into two sublists, one with the elements less than the pivot and the other with the elements greater than the pivot. Next, quicksort is the other important sorting algorithm that is based on the divide and conquer approach. Unlike merge sort, the quicksort, unlike the merge sort, which divides its inputs elements according to their positions in the array, quicksort divides them according to their value. We already encountered this idea of an array partitioning in our previous videos, where we discussed the selection problem. A partition is an arrangement of the array's elements so that all the elements to the left of some element a of s are less than or equals to a of s, and all the elements to the right of a of s is an array, are greater than or equals to a of 0 to s minus 1, which is also like n minus 1, the array length. All are smaller than equals to a of s and a of s plus 1 to a of n minus 1. This all are greater than a of s. Obviously, after partitioning is achieved, a of s will be in its final position in the sorted array, and we can continue sorting the two sub array to the left and to the right of a of s independently. Then by the same method, let us difference with the merge sort, that the division of the problem into two sub problems is immediate and the entire work happens in combining their solutions. Here let us see the partitioning the array, how the partitioning of the array is done. Let us there are three steps. Basically there are three steps. First, choose pivot elements, then rearrange the arrays. Third, we recursively call. Now first step is choose pivot element. The first step in the quicksort algorithm is to choose a pivot element from the array. This pivot element will be used to partition the array into two subarrays, one with the elements less than the pivot and one with the elements greater than or equals to the pivot. Next, second step, rearrange the array. Once the pivot element is chosen, the algorithm will rearrange the elements in the array such that all elements less than the pivot are on the left side and all elements greater than or equals to the pivot are on the right side. Recursive calls. After partitioning the array, the quicksort algorithms make recursive calls on two sub-arrays. This processing continues until the entire array is sorted in ascending or descending order, depends on the user. Choosing the pivot. How to choose the pivot? The first one is by choosing the random selection. Selecting the pivot randomly can lead to a balanced partition. So the best efficient way of selecting or choosing the pivot element is by selecting it as a random element from the array, or choosing the first and the last element. Using the first and the last element as a pivot is a simple but can result in the skewed partition. Median of the three, like taking the center or the middle term of the elements, improve the pivot selections. Next, recursive calls on the partitions. In recursive, we first step is divide. Partitions the array around a pivot element, then we conquer, divide and conquer. So conquer is recursively sort the left and the right partitions. Then the third step is combine, merge the sorted partitions back together. The power of quicksort lays in its recursive nature. Once the array is partitioned around a pivot element, the algorithm makes two recursive calls, one to sort the left partition and one to sort the right partition. This divide and conquer approach allows quicksort to efficiently tackle larger arrays by breaking them down into smaller, more manageable sub-problems. Advantages of quicksort. The quicksort is efficiency. Efficiency is good. The time complexity is around O of n log n. And in-place sorting. The quicksort is an in-place algorithm, meaning it can sort the data without requiring additional memory. It can sort the data in the same memory itself, so the space efficiency also is good in quicksort. Simplicity. The quicksort algorithm is relatively straightforward to implement with a simple recursive function or recursive structure. Parallelization. Quicksort can be easily parallelized, allowing for efficient sorting on multi-core systems. This makes it a powerful tool for handling large-scale data processing tasks. So limitations of quicksorts are, since it is sensitive to pivot selection, the pivot selection have a major impact in the time complexity of the quicksort. The pivot selection should be carefully done for the quicksort. The potential for stack overflow. So the stack overflow is common in the quicksort. Inefficient for small arrays. The small arrays have an inefficient complexity. Now let us see the algorithms. These are the algorithm for quicksort. Here the sorts, first basically sorts a subarray. What does the quicksort do? It sorts the subarray. So the input is subarray of array of A from 0 to n minus 1, defined by left and right indexes L and R. So the output will be subarray from array of length L to R, sorted in non-decreasing order. Let us check. If L is smaller than R, then we partition the array. We split the array into two parts and we store it into the S. Now quicksort recursively calls itself, and again the array is passed from the position 0 to the index 0 to S minus 1 or mid minus 1. We can call it as also the mid element. And the second quicksort recursive function is that we start from S plus 1, which is mid plus 1, till the last bound of the array. So this way the sorting is done. Here the partition carried out. Let us see in the next slide. So this is partition function. For partition function, we basically what we do is partitions a subarray by Orr's algorithms using the first element as a pivot. Let us take the first element as a pivot element. The input is subarray of array of length A of 0 to n minus 1, defined by its left and right indexes L and R. So L must be smaller than R. Now partition, the output will be partition of A of means array of L to R with the split position written as this function's value. Now A of L is stored into P, then L is stored into I. It is initialized. L is initialized with I, and R plus 1 is stored with J. Now we repeat the steps. Repeat. I plus 1 is stored to I until A of I is greater than P. Then again repeat. J minus 1 is stored into J until A of J is less than P. Now we swap A of I and A of J. A of I and A of J is swapped until I is greater than equals to J. Now we swap A of I and A of J. Then we swap A of L and A of J. Then we return, as usually, return J. So this is the algorithm for partition. This is the algorithm for quicksort. So both the algorithms are utilized to perform the quicksort algorithm. Now the time complexity of quicksort is, the time complexity of the quicksort is a critical factor So as we know, the time complexities play a crucial role in getting optimized solution for the problem. The best case scenario, when the pivot element is chosen optimally, then quicksort has a time complexity of O of n log n. So the best case is, or the optimal case is O of n log n, making it an efficiency algorithm. However, the worst case of the scenario is O of n square, which is huge, which is less desirable. This highlights the importance of the pivot in the quicksort algorithm. So let us take an example: 5 3 1 9 8 2 4 7. Now the pivot is given as 5, and the I is traversed till 9, then these both are swapped. 9 and 4 are swapped. Again I is near 8 and j is near 2. Then 2 and 8 are swapped. Again it traversed to, I is traversed to 8 and j is traversed to 2. It is not possible. Now the pivot element 5 and j are swapped. Now the exact position of 5 is in the fourth index. It is correct because when we swap this, when we partition this 2 3 1 4, we get, when we put to left to right, see 1 2 3 4 5, it is exact position of 5. So the fourth index is having the 5 element, which is exact. Now we will take the other element, which is 2 3 1 4. The 2 is the pivot. Again the same process is carried out. Again 2 is swapped. Now 1 2 3 4 is present. Now we combine the partitioned element and we form the quicksort sorted elements. So this is the time complexities. To find the worst case, we do as n plus 1 and n plus 2, n plus 1 to n plus till 3. Now it is sorted as n plus 1 into n plus 2 divided by 2 minus 3. So this is approximately equal to O of n square. This will be like n square divided by 2. So n square is the major term, so n square is taken as common. Now the average case is around 0, and average case will be like around 1.39 n logs 2n, which is also the best case. The best case scenario is O of n log n. So this will be the quicksort's best case will be O of n log n according to the loops and according to the problems. Basically we must take the pivot as the optimal element, because according to the pivot the time complexity depends for the quicksort. So the worst case is O of n square. This occurs when the pivot element is selected at each step is always the smallest or the largest element in the unsorted partitions. And at that time the worst case scenario will be O of n square. So exactly the quicksort will be depends on the pivot element. So better pivot selection methods such as randomized quicksort that uses a random element, or the median of 3 method that uses the median of the leftmost and rightmost and the middle element of the array, switching to insertion sort on very small sub arrays between 5 and 15 elements, and modification of the partitioning algorithm such as the 3-way partition into segments smaller than equals to and larger than the pivot. According to Robert Sidgwick, the author of this book, the world's leading expert on quicksort, such improvements in combination can cut the running time of the algorithm by 20% to 30%, which is huge. So the conclusion and summary is the quicksort algorithm is high efficient sorting technique with a best case time complexity of O of n log n, making it an excellent choice for many practical applications. While it can have a worst case scenario of O of n square, this can be mitigated by carefully selecting the pivot element. Overall, quicksort advantages such as its speed, simplicity and in-place operations make it a widely used and valuable tool in the realm of data sorting and manipulation. Thank you. Have a nice day.